This is the second question in the paper 2016 for SET1 for electrical engineering. It says, consider a 3 by 3 matrix with every element being equal to 1. So let's construct that. Okay. Let's call the matrix as A. It's a 3 by 3, so all the elements are 1 here. Okay. Its only non-zero eigenvalue is dash. Again, this is not a multiple choice question. We will have to find the answer. Okay. So, I hope the writing is visible to you all. Well, so here's the matrix. A equals, this is a 3 by 3 matrix, and the order of the matrix is 3. Order of the matrix is 3. Now the question asks for the non-zero eigenvalue. Okay, so let's call the eigenvalue as lambda. So the non-zero eigenvalue would be equal to the element present. Now each element is equal to 1. Okay, so lambda would be equal to the element present multiplied by the order of matrix. This is actually a nice trick. So that's 1 into 3, which is 3. So here the answer is 3. 3 is the non-zero eigenvalue for this 3 by 3 matrix. Here's the third question. The Laplace transform of the function f of t is equal to e power 2t sine of 5t ut. Now this is a multiple choice question, so we have to be quite careful in choosing the right one. As soon as you see the Laplace transform, you should be familiar with the list of general formulas. Now this function here, f of t is equal to e power 2t sine phi t ut, should tell you that the first thing we do is take the trigonometric part of it. Okay, let's find the Laplace of this part. Now you will recall that the formula for e power at sine omega t is omega divided by s minus a whole square plus omega square. So this is a direct formula. Now you will see that it is exactly similar to the function given to us. I think this is the best way we can do it. So let's take the Laplace of the entire function as it is, e power at sine omega t. Now comparing both of these, we see that the value of a is 2 and the value of omega is 5. Substitute that over here, we'll get 5 divided by s minus 2 whole square plus 5 square. Let's solve further. That's s square plus 4 minus 4s plus 25. Let's see if we will find the answer here. That's s square minus 4s plus 29. And this is the very first option. So that's the answer. Okay, so here's the fourth question. A function y of t such that y of 0 is equal to 1 and y of 1 is equal to 3 e power minus 1 is a solution of the differential equation given. Okay, so here y of 0 is equal to 1 and y of 1 is equal to 3 e power minus 1 are initial function conditions. So let's write the differential equation given here. So that's d square y by dt square plus 2 dy by dt plus y is equal to 0. So we're supposed to find out what y of 2 is. So the next thing we do is write this in the operator function form, which would be d square y plus 2 dy plus y is equal to 0. So what I've done is written d by dt as capital D. Okay, so now let's take y common. D square plus 2d plus 1 y is equal to 0. So this the equation that is there within the brackets is called auxiliary equation. So we take the auxiliary equation and equate it to 0. Okay, so that's the auxiliary equation. D square plus 2D plus 1 is equal to 0. This is a quadratic equation which can be written as a product of factors D plus 1 into D plus 1, which further gives us the values D equals minus 1 and minus 1. Now the roots are the same and the roots are real. So if you recall the general equation for such roots, general equation. Now first we are supposed to find out the particular solution. Okay, the particular solution. In order to find the particular solution, we first find the general equation solution. So that would be in the form e power ax into c1 plus c2x. Here c1 and c2 are constants. Okay, they correspond to the roots that we have over here. So e power ax into c1 plus c2x. Okay, and now let's call this equation 1. I think I can write it on the side over here, so please see. I'll write it here. Okay, so the general equation or the general solution, I'll put that down. The general solution y is equal to e power. Now what is a? A is the root that we have here, minus 1. Okay, so minus 1x times c1 plus c2x. We need to find out what are the values of c1 and c2. So that's our next step. And in order to do that, we take the help of the initial conditions given over here. Okay, so we start with y of 0 is equal to 1. Now when y of 0 equals 1, that means that y is equal to 1 and x equals 0. Now let's substitute that here and see what we get. Okay, so that would be 1 is equal to e power minus 1 times 0 is e power 0, which is again 1, and we get c1 plus c2 times 0. So here we directly get the value of c1. c1 equals 1. Okay, then next let's take the second condition given to us. Y of 1 is equal to 3e power minus 1. So this says that y is equal to 3e power minus 1 and x equals 1, the value that is there within the brackets here. Let's do the same thing. We substitute these values into the general solution. So that's 1 is equal to e power minus 1 c1. Oh, I'm sorry, this is 3e power minus 1, right? So that's the value of y. c1 plus c2. Now we have the value of c1, 1. We can cancel out the exponential functions over here. So that's 3 is equal to c1 plus c2. 3 is equal to 1 plus c2, which gives us that c2 is equal to 2. So we have the values c1 and c2. Now when we substitute this into the general solution, it becomes particular solution. So let me just grab another piece of paper here, write that down. Okay, so I'll write that again. So the general solution is y is equal to, so we have e power minus x, e power minus x, c1 plus c2x. We have c1 equals 1, c2 equals 2, right? Okay, so let's substitute this into the formula above, equation above, and we get 1 plus 2x. So this is known as the particular solution. Okay. Alright, now the question says that we are supposed to find y of 2. So the value of x there is 2. So it says find y of 2. So here this is the value of x. Now let's substitute this x over here and see what we get. We get y is equal to e power minus 2 into 1 plus 2 times 2. So that's y equals e power minus 2 and 5. 5 e power minus 2. And 5 e power minus 2 is option B. That's your final answer. This is the fifth video. The value of the integral, closed integral, 2z plus 5 divided by z minus 1 by 2 times z square minus 4z plus 5 dz over the contour mod z is equal to 1 taken in the anti-clockwise direction. So there are three things that we need to see, note exactly in the question. The first is that this is the closed integral. The contour is the closed curve. Mod z is equal to 1. And it has been taken in the anti-clockwise direction. So we begin by finding the value of the integral by working on the singular points. So the singular points can be found by equating the denominator to 0. Okay. So we find the singular points equating the denominator to 0. So let's do that. Z minus 1 by 2 times z square minus 4z plus 5 is equal to 0. Now with this we immediately get the first root, z is equal to 1 by 2. So this is the first singular point. Now we will have two more points from the second bracket, z square minus 4z plus 5. Now this is a quadratic equation, and this quadratic equation can be solved by using the quadratic formula. Now you're already quite familiar with that. We worked that out in the very first question of this paper set. You can use that. So minus b plus or minus root of and so on and so forth. So I'll leave that solving part to you, and I'll write the singular points over here. The points are 2 plus or minus I. So 2 plus I, 2 minus I. These are the two roots and they are complex roots. So you will have to note that. So z is equal to 1 by 2 is the only real root here. And you will notice that in the given curve, mod z is equal to 1, closed curve, z is equal to 1 by 2 is the only point that lies within this curve. So this is the value that we will have to use. Z is equal to 1 by 2. Okay. And to solve this integral, this function, we are going to use Cauchy's integrated formula. Cauchy's integrated formula. Okay. So in order to use this, what we are going to do is find the value of the integral by substituting the real value that we have found, the singular point that we have chosen, z is equal to 1 by 2, into the part of the function that is remaining, apart from this. So we leave this factor out and we substitute z is equal to 1 by 2 into the other, into the variables that are there, other than this factor here. So that would be 2z plus 5 divided by z square minus 4z plus 5 at z is equal to 1 by 2. Okay. So in order to do this, we have, the formula says 1 by 2 pi I times this, 2z plus 5 divided by z square minus 4z plus 5 at the value z is equal to 1 by 2. But here is where you will have to note that the question says anti-clockwise. Now because the question says anti-clockwise, this term is taken to the power of minus 1. So 1 by 2 pi I becomes 2 pi I. That's why you will notice that in each of these or at least in these two, you will notice that the term pi I is in the numerator. So here we will have to take the reciprocal. So let me just grab another piece of paper here to continue. Okay, so we have Cauchy's integrated formula, and let me write that down again. So we took the reciprocal, so that would be 2 pi I into the value of 2z plus 5. 2z plus 5 divided by z square minus 4z plus 5 at the value of z is equal to 1 by 2. Okay, so let's substitute and see what we get. We get that's 2 pi I times 2 into 1 by 2 plus 5 divided by 1 by 2 square minus 4 times 1 by 2 plus 5. Okay, so this is quite basic arithmetic, and I'm going to leave that part out to you and see what you get. I'm just going to do that directly. 2 pi I times, okay, so the numerator is going to be 6 divided by, okay, and the denominator would be, let's see, that's a square, minus 4, then that's 2. Okay, so we'll get here 13 by 4. Okay, so you solve that further to get 2 pi I times 24 by 13. And finally, we get 48 pi I by 13. So this is the value of the closed integral, and this option matches part B. That is the final answer. Welcome back. Here's the sixth question. It says the transfer function of a system is y of s divided by r of s, transfer function, s by s plus 2, and the steady state output y of t is a cos 2t plus phi for the input cos 2t. The value of a and phi respectively are. So we are supposed to find out what a and phi is in the output given, y of t. Okay, so let's start with the transfer function given to us. So the transfer function y of s divided by r of s is equal to s by s plus 2. Now we can use a direct formula over here. Okay, so the formula says, let me write that down. The formula is h of omega, so we're converting that, okay, is equal to omega by root of omega square plus a square. Now this is the formula. When we compare this, a is 2, okay, so here a is 2. Now let's substitute that into this formula over here. So we will get h of omega is equal to omega by root of omega square plus 4. Now we need the phase as well, because we are asked the value of phi, so we need a phase angle. Now the formula for phase angle over here is 90 minus tan inverse of omega by a. Now we know the value of a from the given function, which is 2. So phi would be 90 minus tan inverse of omega by 2. Now in order for us to find out the value of phi, we need the value of omega. So that's going to be our next step. We need the value of omega. So let's go back here to the output given. The output given is y of t a cos 2t plus phi. And the input, this is the output, and the input is cos 2t. Now, in general, trigonometric functions are denoted as cos omega t, sin omega t, and so on and so forth. So, from the input function given to us, it is quite easy to identify that the omega here is 2. Okay, so omega here is 2. Now, if we substitute this here, let's see what we get. We get h of 2 is equal to 2 divided by root of 4 plus 4. that would be 2 by root 8, which can be written as 1 by root 2, because root 8 is 2 root 2, 2 and 2 cancels, we have 1 by root 2. So we have what h of 2 is, or h of omega. Okay. Next, we can substitute the value of omega over here and directly find what is the phase angle. So we have that phase angle phi, let me write that down here, is equal to 90 minus tan inverse of 2 by 2. Now 2 by 2 is 1. Let me just grab another sheet of paper here. Okay. So we have h of omega is equal to 1 by root 2 and phi is equal to 90 minus tan inverse of 2 by 2, which is tan inverse of 1. And you know what tan inverse of 1 is, right? Tan inverse of 1 is 45 degrees. So phi is equal to 90 minus 45, which is 45. This is a positive value. So all in all, h of omega can be written as 1 by root 2 angle 45 degrees. Okay. So this, the magnitude 1 by 2 corresponds to A, and the angle 45 degrees corresponds to phi. So these are the final answers. Now let's check and see which option it matches. It matches B. B is your final answer. Here's the 7th question. The phase crossover frequency of the transfer function given g of s is equal to 100 over s plus 1 cubed in radians per second is one of the 4 choices. Okay, so in order to do this, we need to find out first what in general is the stability condition equation. So that can be considered as a formula. Okay, so stability condition is given by g of j omega, which is minus 180. Now that is standard, alright. So here angle of j omega is the phase angle. We need to find out what is the phase crossover frequency, which is omega. Okay, so let's observe what has been given in the transfer function, which is 100 over s plus 1 whole cube. Now this can further be written as j omega is equal to minus 3 tan inverse omega. Now that is because here we have the power as 3, 100 over s plus 1 to the power of 3 minus 3 tan inverse omega. Now we have that the phase angle is minus 180 from the stability condition. Let's substitute that over here. 180 is equal to minus 3 tan inverse omega. Solving for omega. So we get omega is equal to tan inverse of, so that's just tan of 60. 180 divided by 3, so that's 60. So tan of 60 is root 3. So this matches the very first option. So the phase crossover frequency is root 3. You should be able to convert the transfer function given into an equation according to the stability condition. So because it is 100 divided by s plus 1 to the power of 3, that's s plus a to the power of n, you can write it as minus 3 tan inverse of omega. So I hope this has helped. Let's go to the next question. Here is the 8th question. Consider a continuous time system with input x of t, output y of t, given by y of t is equal to x of t times cos of t. So we have our 4 options saying that this system defined by this equation or defined by the output given is linear and time invariant, non-linear and time invariant, linear and time varying, and non-linear and time varying. So basically we have two aspects to work here. We have to check the linearity of the system given, and we have to find a check on the time invariance of the system given. Okay, so those are the two factors. The first is linearity, and the second is time invariance. Okay, so there are two conditions to say that the system is linear. One condition is that it must be homogeneous, and the second is that it has to satisfy the additive property. So let's work on linearity first. Okay, linearity property. The function given to us is y of t is equal to x of t cos t. So in order to see if this equation is additive, let's take two conditions. Now the first one, y1 of t, let's assume two different variables. y1 of t is equal to x1t cos t, and the second is y2 of t is equal to x2 of t cos t. x1 of t corresponds to y1 of t, x2 of t corresponds to y2 of t. Now if we add both of these, let's see what we get. So we add the left hand side, y1 of t plus y2 of t, that would give us x1 of t cos t plus x2 of t cos t. We can take cos t common, x1 of t plus x2 of t into cos t. Okay, now let's assume that x1 of t and x2 of t, the addition of both is x of t. Okay, so let me write that down over here. Let x1 of t plus x2 of t equals x of t. So let's plug that in. So we have y1 of t plus y2 of t is equal to x of t into cos t. This is x of t times cos t. But what is x of t times cos t? That is the very function that is given to us in the question, y of t. So we substitute this over here and we will obtain y1 of t plus y2 of t is equal to y of t. So if we add two possibilities, y1 of t and y2 of t, we obtain the original y of t. So this satisfies the additive property, and therefore the given system is linear. The system is linear. Now let's check on time invariance. Let me just take another sheet of paper. Okay, just so you know, now because it is linear, that removes two of the options here. So we are left with either A or C. So we have to see if the given equation or the given system is time invariant or time varying. So basically, if the system has been given a certain delay in time, a delay in the input signal, so we have to check if it still changes as an entire function or it doesn't change. So we have to check on that. Either it changes or it doesn't change. So that's time invariance. Okay. So let's consider y1 of t is equal to x1 of t times cos t. Now if, let's take this part here. If the input, if x1 of t is x times t minus tau. Now here this tau is the delay in input signal. Delay in input signal. So we are giving a certain delay to the function, to the input. So x1 of t is equal to x times t minus tau. Now let's substitute this in place of x1 of t, and let's see what the equation becomes. y1 of t, the output becomes x times t minus tau cos t. Let's call this equation 1. Now, so this delay, let's apply this delay to the function given to us in the question, the original equation. Okay, the original equation says y of t is equal to x of t cos t. Okay, in place of t, wherever t is there in this equation, let's plug in t minus tau. So we are applying the delay in the entire equation. So that's y of t minus tau is equal to x t minus tau cos t minus tau. So in the original equation where t is there, we plug in the delay t minus tau here, here and here, and we get this second equation. Now observe the first equation, the second equation. Are they same? They aren't. y1 of t is not equal to yt minus tau because the delay here is applied only to the input signal and it doesn't correspond to the entire equation, but here it corresponds to the entire equation, the input and the output. So we see that y of t here, y1 of t is not equal to yt minus tau. So when we give the delay, it is not equal to the equation given to us, the function given to us. So that means that it is a varying system, a time varying system. Time invariant is when both are the same. So this is time varying. Now let's check. It is linear and it is varying. So that's option C. So here is the final answer. I hope it has helped. Here is the 9th question. The value of integral minus infinity to infinity e power minus t delta 2t minus 2, where delta t is the Dirac delta function. I hope I'm pronouncing that right. Dirac delta function. And here are the 4 options. So in order to solve this, they have already given us the definition that delta t is the Dirac delta function. So we can use a property of the impulse function. So the property is shifting. It's called shifting. Shifting property of impulse function. Okay, so according to this function, the integral from minus infinity to infinity f of t delta t minus t naught dt is equal to f of t at t is equal to t naught. So the value of t naught is substituted in the function f of t in order to get the value. So this is known as shifting property of the impulse function. Now if you observe the left hand side of the property to the function given to us, you will see that it is very similar. It is exactly the same, so we can actually use it. So this is minus infinity to infinity e power minus t delta 2t minus 2 dt. I think I missed a dt here. Right. Okay, so let's see how we can make this, we can simplify this further. So we can write this as minus infinity to infinity e power minus t. I'm going to take 1 by 2 out, delta t minus 1 dt. Now this gives us t minus 1. So t minus 1 meaning that t naught is 1. So from here we obtain that t naught is 1. So let's substitute into f of t. Now what is f of t here? E. Okay. So that is, we'll have to take this entire function. E power minus t by 2 at t naught is equal to 1. So that's e power minus 1 by 2. And e power minus 1 is 1 by e. So we just take this to the denominator. So the value is 1 by 2e. And 1 by 2e matches the option A. So in most of these questions you will notice that there is a very clear formula or a very clear property with which you can compare the given function with. So make sure that you have all of those points in a sheet of paper so that you can go through it right before the exam. It helps a lot. Well, I hope this solution for this video has helped. Here's the next question. A temperature in the range of minus 40 degrees centigrade to 55 degrees centigrade is to be measured with a resolution of 0.1 degree centigrade. The minimum number of ADC bits required to get a matching dynamic range of the temperature sensor is, now we have our four options. Okay, so the first thing we have to do is to note down the range over here and the resolution given. Now since it is the resolution, what we can actually use is the resolution formula. The resolution formula. Resolution equals T max, maximum temperature, minus T minimum, minimum temperature, divided by 2 power n, where this n is the number of bits. That's what we're supposed to find. We're supposed to find the total number of bits. So T max minus T minimum is the difference or the temperature difference that is given to us. And R is the resolution which has been given as 0.1 degree centigrade. So let's plug those in. 0.1 is equal to 55 minus of minus 40 divided by 2 power n. So basically all we have to do is just solve for n. So what do we have here? Here we have 0.1 which is equal to 95 by 2 power n. And 2 power n is equal to 950. So we can use logarithms here to solve. Let me just write that down here for you. If you recall, if a power m is equal to x, then m is equal to log x base a. So if we utilize this to our equation here, we will get 2 power n is equal to 950. So n is equal to log of 950 base 2. And that comes around to about 9.89. And 9.89 is close to 10. You can round it off to 10. So the answer here is 10. 10 ADC bits. Okay, so here's the next question, number 12. A transistor circuit is given below. The Zener diode breakdown voltage is 5.3 volts as shown. Take base to emitter voltage to be 0.6 volts. The value of the current gain beta is dash. So this is not a multiple choice question and we will have to work it out and find the answer. So first let's look at the diagram given to us, the figure given to us, the circuit here. So here we have the Zener diode and here's our transistor. So this would be base, collector and emitter. So let's take the current passing through here as IE, which denotes the emitter current, and the current passing through here as IB. And now I've taken 0.5 milliamps that is passing through here as I2, and the current that is coming through this branch here as I1. Okay, so these are the various aspects that we need to work on. We have to find, in fact. So they asked us to find the current gain. Now in general, we know that the formula for current gain, IE, is equal to 1 plus beta IB. So we need the emitter current and the base current in order to find the current gain. So let's start with VB. This is the base voltage. The base voltage is given to us as 5.3 volts. Okay. and VE, or the emitter voltage. The emitter voltage is VB minus VBE, or the base to emitter voltage is given to us as 0.6 volts. So that's VBE. VE is equal to VB minus VBE. Okay, so that would be 5.3 minus 0.6, which would be 4.7 volts. So that is VE. The next in line is IE. So let's find the current of the emitter over here. So IE is equal to the voltage VE divided by the resistance that it passes through. So the resistance in this branch is 470. Voltage by resistance. And that gives us 10 milliamps. So we have IE. Next we need IB. So in order to find IB, we need to know what I1 is. So we can use this node over here. In order to find IB, we can use KCL at this node. So we know what I2 already is. Now we need I1. So I1 is equal to 10 minus 5.3. You know that. The difference between the voltages divided by the resistance in that branch. So that would be 4.7 into 10 power 3 kilo. Be very careful with your units. So that's 4.7 K, and that would be 4.7 into 10 power 3. So if we solve this, we'll get 1 milliamp. So I1 is 1 milli, I2 is 0.5, so we will be able to find out what IB is. Now at this node, we apply KCL, Kirchhoff's current law. Now Kirchhoff's current law, the incoming currents would be equal to the outgoing currents. So that, let's write that equation down here. I1 is equal to I2 plus IB. Or in other words, IB is equal to I1 minus I2. So I1 minus I2, 1 milli minus 0.5. So IB is 0.5 milliamps. IB is 0.5. We have IE as 10. Now we substitute both into this and find out what our final answer is. Let me just take another sheet of paper here. Okay, so we have IE. IE is equal to 10 milliamps. We have IB, which is 0.5 milliamps. And now we have the formula to find out the gain. IE is equal to 1 plus beta into IB. Let's substitute. That's 0.5 into 10 power minus 3. 1 plus beta into... Oh, I'm sorry, I made a mistake here. That's 10. 10 into 10 power minus 3. And here we have 0.5 into 10 power minus 3. So we can remove the extensions of 10 power minus 3 on both sides, and we'll be left with 10 is equal to 1 plus beta into 0.5. And that would be 10 divided by 0.5 is equal to 1 plus beta. And we would have here 20 is equal to 1 plus beta. Therefore, beta is equal to 20 minus 1, 19. Beta is equal to 19. This is your current gain. Let's see if the option, oh right, there are no options here. So our final answer would be 19. I hope this has helped. Okay, so here's question number 13. In cylindrical coordinate system, the potential produced by the uniform ring charge is given by phi is equal to function of r comma z, where f is a continuous function of r and z. Let E be the resulting electric field, then the magnitude of delta cross E, A increases with r, is 0, is 3, decreases with z. Okay, so here we need to analyze the question given to us. Now, notice that the charge is not varying with time. They have mentioned that E is the resulting electric field, where F is a continuous function. and it is a uniform ring charge. So this indicates that the charge is not varying with time, and E, or the electric field, is static. So that is a very important point here. The charge is not varying with time. Since the charge is not varying with time, the electric field given to us is static. Now, when the electric field is static, delta cross E is 0. And therefore, the answer is B, 0. Here's the 14th question. A soft iron toroid is concentric with a long straight conductor carrying a direct current I. Okay, so as you're reading the question, it always helps if you can figure out a diagram or to draw a diagram as you're reading it. So here we have a soft iron toroid is concentric with a long straight conductor carrying a direct current. Okay, so let me draw two concentric circles here. Okay, so there's our toroid. This entire portion here is the soft iron. Okay, and so it says that if the relative permeability mu r of soft iron is 100, the ratio of the magnetic flux densities at two adjacent points located just inside and just outside the toroid is. Okay, so we need one which is inside the toroid and one which is outside. So we can take a point inside and one point which is outside. Alright, so here the relative permeability is given as mu r. So we have mu r. You should also know that mu naught comes along with that. So this is our permeability of air, and of soft iron is 100. So this is 100. Okay, so mu r is 100. Mu naught is, well, let's just keep it the way it is. We don't need to substitute any value here. Now we have been asked the ratio of the magnetic flux densities at both of these points. So let's write down what the magnetic flux density inside the toroid first, and then we will write the magnetic flux density outside. So the magnetic flux density inside the toroid, which is concentric to the conductor carrying the current, would be mu naught into mu r times I divided by 2 pi r. Now because the conductor carrying current is a circle, the circumference is 2 pi r, and mu naught times mu r is the permeability, relative permeability times the permeability of air into the current that is passing through the conductor. So this is the general formula. So this is inside, whereas outside the toroid, mu r will not apply here because it is not inside, right? It is outside. So there is no soft iron over here. It's just free air. So here we wouldn't involve mu r in the second formula. It would be mu naught I by 2 pi r. Okay. So next we have, we need the ratio. The question says ratio of the two magnetic fluxes. So it would be inside to the outside. So it's the ratio between these two, and you can immediately see that they cancel out. Everything cancel out except for mu r. Right? Let me write that down here. So that's mu naught, mu r I divided by 2 pi r divided by, it's a ratio, mu naught I by 2 pi r. So the denominators go off, mu naught I as well. So we are left with mu r. So the ratio of the magnetic flux densities of the inside to the outside is mu r, and the value of which is given to us as 100. So the answer is 100. I hope this has helped. Here's question number 15. RA and RB are the input resistances of circuits as shown below. So we have two circuits here. RA is the input to this circuit, RB is the input resistance to this circuit. The circuits extend infinitely in the direction shown. So they continue on this way. So this circuit will continue on with 1 ohm resistor here, 2 ohm resistor there, and so on. Which one of the following statements is true? RA equals RB. Now let's analyze both of them. Now we clearly see that there is a difference, right? So here the circuit starts off with a 2 ohm resistor on top. But here it starts off with a 1 ohm resistor between the 2 points. So they are not equal. RA cannot be equal to RB because it has an extra resistance in the start over here. Now they definitely cannot be equal to 0 because they do have values, because they extend on to infinity. So which leaves us with option C and option D. So it is one of these two. Now we have to look at both of these circuits and try and analyze. You will notice that this portion is exactly same with this here. Everything except for this 1 ohm resistor in the beginning is the same with the first circuit over here. So this implies that RB is equal to the entire circuit RA. This entire circuit is RA, right? So that's RA, which is in parallel with the resistance 1 ohm resistance. So they are in parallel. So that's the only thing that is added here. And to solve this, we know that 1 by RB is equal to 1 by RA plus 1 by R of 1 ohm. So that's 1 by RB is equal to 1 by RA plus 1 by 1. So if we solve this, we solve it for RB. Okay, let's solve and see. Let me just take another sheet of paper here. Okay. So we have RB is RA parallel to R of 1 ohm. And you know the formula there. The formula of the resistance or the total resistance is 1 by R is equal to 1 by R1 plus 1 by R2 plus so on and so forth. So here we have 1 by RB is equal to 1 by RA plus 1. So we solve this. 1 by RB is equal to 1 plus RA by RA. We flip it over, reciprocal. RB equals RA by 1 plus RA. And you will notice that this relation is the fourth option right here. So it all comes down to your observance of the circuits. So do keep that in mind, and I hope this has helped. This is the next question, number 16. In a constant V by F induction motor drive, the slip at the maximum torque, the options are, is directly proportional to the synchronous speed, remains constant with respect to the synchronous speed, has an inverse relation with the synchronous speed, and has no relation with synchronous speed. So basically, we need to know the relationship between the maximum torque and synchronous speed. Okay, so when we talk about induction motor drive, the slip is written in terms of R2 divided by X2, where R2 is the rotor resistance and X2 is rotor reactance. And you should also know that this ratio is per phase. It's written in terms of per phase, and the motor is at standstill. Now the rotor reactance can be expanded in terms of angular frequency and inductance. So X is equal to J omega L. If we place this in the ratio here, we will obtain slip equals R2 divided by J omega L2, where omega is the angular frequency and L is the inductance. Now further, angular frequency can be written in terms of frequency, f. So we know that omega is 2 pi f. Let's substitute that over here. We'll get slip is equal to R2 by J2 pi f L2. So according to this, the slip is inversely proportional to f. We see that here. Slip is inversely proportional to frequency. Now frequency can also be related in terms of speed. Now let's check that. Here we have synchronous speed 120 f by p. I'm sure that you're familiar with this formula here. Synchronous speed is 120 f by p. Here the synchronous speed is directly proportional to frequency. So that means frequency directly proportional to synchronous speed, which further implies that slip is inversely proportional to the synchronous speed. So this is the final answer, which means that the right option here has an inverse relation with the synchronous speed, number C. I hope this has helped. Here's the next question, number 18. In this given circuit, the current supplied by the battery in amps is dash. Again, this is not a multiple choice question, so you will have to work it out. So the circuit given shows that we are supposed to find out the value of I1, because it's the current supplied by the battery, and we see that I1 is the current that is coming out of the battery. So I1 is the value we need to find. Okay, so we also have I2 for the source over here. So let us begin by working on KCL at this point here. Now let me call this A. Okay, so KCL at A. Just so you know, KCL is Kirchhoff's current law. So Kirchhoff's current law at A states that the incoming currents at the node equals the sum of the outgoing currents. So here we have I1 incoming at the node and I2 outgoing. So which means I1 equals to I2. So that's our first relation. Okay. Now that we have found the first relation, let's apply Kirchhoff's voltage law at the outer boundary of the entire circuit. Okay. So Kirchhoff's voltage law at the outer boundary. Okay, so let's see what we get here. We have the voltage here from the battery 1 minus, and the current passing through this resistor here. So we have that's 1 into I1. So voltage, right? So voltage is I times R, resistance I1 times I1 minus. Then now we come here. So the voltage across this, that's 1 times I2. 1 into I2. We have another resistor here. So that's again 1 into I2. Note that the 1 here, they are all the resistance values. Okay, is equal to 0. So this is our KVL equation. Let's solve and see what we get. We get 1 minus I1 minus I2 minus I2 is equal to 0. So that's 1 minus 2I2 minus I1 equals 0. So we can use this relation here and apply it into this relation here. So let's substitute. Instead of I1, we substitute that. We get 2I2. So 2I2, that comes to minus 4. I2 is equal to 0. And the value of I2 is 1 by 4 amps. Now that we have I2, we can substitute this value here and find out what I1 is. So I1 equals 2 times I2. 2 times 1 by 4. That gives us I1 equals 1 by 2.5 amps. So the final answer is 0.5. I hope this has helped. So here's the next question, number 19. And the question reads, in a 100 bus power system, there are 10 generators. Let me just underline that so that we know what we're dealing with. We have 100 bus power system and we have 10 generators. In a particular Newton-Raphson load flow technique in polar coordinates, 2 of the PV buses are converted to PQ types. So we have 2 PV buses that are converted to PQ. In this iteration, the choices are the number of unknown voltage angles increases by 2 and the number of unknown voltage magnitudes increases by 2. So you will notice that in each option, we are dealing with 2 things, voltage angles and voltage magnitudes. These are the 2 with different combinations, and we'll have to find out exactly which one is right. So option A says that the number of unknown voltage angles increases while the voltage magnitudes increases by 2 as well. Option B says voltage angles remain unchanged whereas the unknown voltage magnitudes increase. In C, it says that the voltage angles increases and voltage magnitudes decrease by 2. And the final one says that the voltage angles remains unchanged and the number of unknown voltage magnitudes decreases by 2. All in all, we have 2 aspects, voltage angles and voltage magnitudes. So let's see, so the total number of buses are 100 given to us and there are 10 generators. So that immediately tells us that the number of load buses would be 100 minus 10, which is 90. So I'll note that down right here. So we have total number of buses 100, number of generators 10, which means number of load buses is 100 minus 10, 90. So there are altogether 90 load buses. Now you should know that at every load bus, the voltage magnitude and the voltage angles must be calculated. Both must be calculated. Both aspects that are given in all of these 4 choices. So at every generator bus, so this is at every load bus, okay? At every load bus, we need to calculate the magnitude, the voltage magnitude, as well as the voltage angle. And for every generator bus, we need to calculate Q and delta must be calculated as well. Now at all the buses, delta will be calculated. So it shows that for load, though there is a change, but the angles need to be calculated nonetheless. So this means that no matter what kind of bus it is, we need to calculate the angle, the voltage angle. So this means that there is no change in the voltage phase angle calculation. There's no change, okay? So the unknown voltage angles does not increase, it remains unchanged. So this is our Q here, okay? So the voltage angles remains unchanged because we need to calculate no matter what kind of bus it is. Then next it comes down to the voltage magnitude, whether it increases or decreases. Now the question says that it is Newton-Raphson load flow technique. Now during the iteration, 2 generator buses are converted to PQ type. So that means that 2 generator buses change to load buses. So 90 becomes 92. So we are adding here, it becomes load buses. Both those 2 PV buses are changed to load buses. So 90 becomes 92. So that means that the voltage magnitudes increase by 2. So the right option here is increases by 2, here B. The number of unknown voltage angles remains unchanged and the number of unknown voltage magnitudes increases by 2. I hope this has helped. Here's the next question, number 20. The magnitude of three-phase fault current at buses A and B of a power system are 10 pu and 8 pu respectively. Neglect all resistance in the system and consider the pre-fault system to be unloaded. The pre-fault voltage at all buses in the system is 1 pu. The voltage magnitude at bus B during a three-phase fault at bus A is 0.8. And the voltage magnitude at bus A during a three-phase fault at bus B is dash. So this is not a multiple choice question. We will have to work the question out. So the best way to go about this is to first see how we can put this in a rough diagram. So I have drawn a rough diagram over here, considering A and B here are the buses. Okay, and we have that the pre-fault system is unloaded, and at each it is 1 pu. The pre-fault voltage at each bus is 1 pu. So we have 1 pu at each bus. And next we have the voltage at bus B after a three-phase fault at A is 0.8 given to us. So now let us find out what is the voltage at B, at bus B. Let's call that VB. Now the general formula is this: VB equals to V pre-fault voltage minus Z12 times the fault current at B. Okay, so that's what we have so far. Now we need to find out what is the value of this mutual impedance over here, Z12. So we plug the values in. VB is 0.8, pre-fault voltage is given to us as 1 minus Z12 times 8. That's the fault current given to us at B. We are finding out for B, therefore we need the value at B. Okay, so if we solve this and find the corresponding value for Z12 would be, let's see now, 1.0 minus 0.8 divided by 8, and that gives us 0.025 pu. Yes, okay. And then now that we have Z12 is the same as Z21, so we can apply the same formula for VA. Now the question says the voltage magnitude at bus A during a three-phase fault at B. Now let's say there is a fault at B, so we will have to find out what is the voltage magnitude at A. So the formula now becomes VA is equal to V pre-fault minus Z21 times IF of A. Let me just write that here. Okay. So we have here VA now is V pre-fault minus Z21 into IF of A. So that would be, we need to find VA, right? So 1 minus, now we found this to be 0.025 times 10. 10 is what is given in the question. So that's 10. Right about there. 10 pu. Okay. So let's solve. We'll get 0.75 pu. So the answer here is 0.75. I hope this has helped.